Hi, welcome to our third project video. My name is Hyun-mo,
And I'm Yeon Kim.
and today we will introduce how we built our flip-flop based counter and finite state machine.
After that, we will show you 6 demonstrations using the Basys3 board. Let's get started. So we will start from divide by n counter to implications. As a student A, I designed the NETDFF using only NOR gates. I first designed a D-latch. In the original D-latch structure, clear, D, and D var were connected using AND gates. However, I replaced the AND gate structure with an inverter in NOR gates because it follows the same logic. After that, I connected two D-latches together to make a T flip-flop. This T flip-flop was then used in my counter later. So I raised the N up to 100 million counter so it can measure 1 second. As you can see in the simulation, in the negative edge, it will restart another period for 1 second. So it can actually be the basic of the clock. Next, I designed the Christmas tree LED pattern on the Basys board. To make the LEDs look like a Christmas tree, I used the different blinking patterns of AND in exclusive OR operations. The AND operation has a longer off period in its duty cycle, so some LEDs stay off longer. On the other hand, the exclusive OR gates, they make the LED blink more irregularly, almost like twinkling lights. I arranged the Christmas tree from the star at the top to the trunk at the bottom. On the Basys board, I assigned the center LEDs to the top of the tree and the outer LEDs to the lower parts of the tree. As a result, the center LEDs blink more fastest, while the LEDs near the edges blink more slowly. I will demonstrate this directly on the Basys board later.
This slide shows the inner diagram and test result of the D-latch and PTDFF, which we built using only NAND gates. We confirmed that the reset and hold modes work perfectly. Next is the diagram and wave result for the 1 second counter. You can see the register counting exactly 100 million times, then resetting to make a 1 second pulse. Following that, we have the complex diagram and test for the Christmas tree controller. The result shows that clock with different speeds work stably at the same time.
So let's move on to the second part. For the FSM part, I designed an 8-state 2-input FSM using binary code. The 8 states represent different volume levels. The 2 inputs represent volume up and volume down. So when the input is volume up, the state moves to a higher volume level. When the input is volume down, the state moves to a lower volume level. After completing the 8-state FSM, I expanded this design to 16 states. This allowed the volume level to be controlled in more detailed steps.
Next is the FSM design based on gray code. Using the truth table, we drew 4 variable column maps to get the logic formulas for D2 and D1. On the right is the hardware diagram built using only pure logic gates. Finally, this is the state diagram and the combined diagram of the 8-state FSM using gray code. Because gray code only changes 1 bit at a time, we reduced logic waste and greatly improved stability.
So let's see our actual Basys3 board operations. First, this is counter design. Hopefully it seems like Christmas tree for you guys. As I explained earlier, the LEDs in the center blink more faster and the LEDs near the edges blink more slowly. While I press the the reset button, the LEDs connected to the end and buff operations remain on, while the LEDs connected to the XOR operation remains off. Ta-da! So we can check that each LED is correctly connected to its operation. Second, this is the 8-state 2-input FSM. If I move the switch up or down and then press the step button, the value increases or decreases depending on the input X. As you can see, it doesn't go up if it hits limits or go down. This is 16-state 2-input FSM. Unlike the previous 8-state FSM, this one can count up to F. Also, I assigned each Q value to the 4 LEDs on the right side, so we can directly check the output as a 4-bit binary value.
This Christmas tree circuit uses the frequency division of counters. We divide the 100 MHz main clock into 4 different blinking speeds by arranging them symmetrically from the center. We created this 3D blinking effect. Start from the 0 state. Let's press the up button. As I keep pressing it, you can see the state increasing step by step. The LED gauge fills up like stairs until it finally reaches the top, displaying 7 full. If we press both the down and reset buttons together, it instantly resets to 0. Pressing up and down together skips all steps and jumps straight to max. Finally, if we press the down button while in this maximum state, the system resets and immediately returns to 0.
As I wrap up this semester, this project had the most significant impact on me. I realized that I improved much more than I expected compared to March. The projects were challenging every time, and in the beginning, I didn't even know what the binary number was. However, step by step, I learned how to design multipliers, counters, FSMs, and extra basis board operations. Thomas Edison once said, I love this quote: "Genius is 1% inspiration and 99% of perspiration." I'm not sure if I have that 1% of inspiration yet, but I still want to keep grinding. This project showed me that possibility, so I'm thankful about that.
By implementing a sequential logic circuit on actual hardware, I was able to highly develop my particle sense for system semiconductor design. Troubleshooting and optimizing the circuit was challenging, but seeing the board operate exactly as intended gave me a deep sense of accomplishment.
So let's wrap up this presentation too. We start with basic logic gates like AND and OR gates, and we build flip-flop, and eventually we develop it into extra counter. So Hyun-mo and I developed 2 different counters, so you can see the Basys3 operate differently.
Next is our FSM design. We upgrade the exciting 2-input 8-state structure to a 4-input 8-state FSM to control a wider variety of conditions. Additionally, we changed the state assignment from binary code to gray code. Through this, we were able to significantly simplify and optimize the final logic equation derived from the kernel maps.